right, well, we've been looking at a couple of examples of stream programming. All the stream procedures that we've looked at so far have the same kind of character. We've been writing these recursive procedures that kind of generate these stream elements one at a time and put them together in const streams. So we've been thinking a lot about generators. There's another way to think about stream processing, and that's to focus not on programs that sort of process these elements as you walk down the stream, but on things that kind of process the streams all at once. Let's see, show you what I mean. Let me start by defining two procedures that'll come in handy. The first one's called add streams. Add streams takes two streams, S1 and S2, and it's going to produce a stream whose elements are the consecutive sum, or the corresponding sums. Right? We just sort of add them element-wise. If either stream is empty, we just return the other one. Otherwise, we're going to make a new stream whose head is the sum of the two heads, and whose tail is the result of recursively adding the tails. Right, so that'll produce the element-wise sum of two streams. And then another useful thing to have around is scale stream. Scale stream takes some constant number in a stream S and is going to produce the stream of elements of S multiplied by this constant, and that's easy. That's just a map of the function of an element that multiplies it by the constant, and we map that down the stream. Okay, so given those two, let me show you what I mean by programs that operate on streams kind of all at once. Let's look at this. Suppose I write this. I say define, I'll call it ones to be const stream of 1 onto ones. And what's that? That's going to be an infinite stream of ones, because the first thing is 1, and the tail of it is a thing whose first thing is 1, and whose tail is a thing whose first thing is 1, and so on and so on and so on. So that's an infinite stream of ones. And now using that, let me give you another definition of the integers. We can define the integers to be, well, the first integer we'll take to be 1, it's const stream of 1, onto the element-wise sum, onto add streams of the integers to ones. Okay. The integers are a thing whose first element is 1, and the rest of them you get by taking those integers and incrementing each one by 1. So the second element of the integers is the first element of the integers incremented by 1. And the rest of that is the next one, and the third element of that is the same as the second element, as the first element of the tail of the integers incremented by 1, which is the same as the first element of the original integers incremented by 1 and incremented by 1 again, and so on. Right? That looks pretty suspicious. See, notice that it works because of delay. See, this looks like, let's take a look at ones. This looks like it couldn't ever even be processed, because it's suddenly saying, in order to know what ones is, I say it's const stream of something onto ones. The reason that works is because of that very sneaky hidden delay in there. Because what this really is, remember, const stream is just an abbreviation. This really is const of 1 onto delay of ones. So how does that work? You say, I'm going to define ones. First, I see what ones is supposed to be defined as. Well, ones is supposed to be defined as a const whose first part is 1 and whose second part is, well, it's a promise to compute something that I don't worry about yet. So it doesn't bother me that at the point I do this definition, ones isn't defined. Having run the definition now, ones is defined. So that when I go and look at the tail of it, it's defined. It's very sneaky. And then integers the same way. I can refer to integers here because hidden way down because of this const stream. It's the const stream of 1 onto something that I don't worry about yet. So I don't look at it and I don't notice that integers isn't defined at the point where I try and run the definition. Okay, let me draw a picture of that integers thing because it still maybe seems a little bit shaky. What do? I've got this stream of ones, and that sort of comes in and goes into something, into an adder. That's going to be this add streams thing. And that goes in, that's going to put out the integers. And the other thing that goes into the adder here is the integers. So there's a little feedback loop. And all I need to start it off is someplace I've got to stick that initial 1. Right. In a real signal processing thing, this might be a delay element that was initialized to 1. But there's a picture of that ones program. And in fact, that looks a lot like, if you've seen real signal block diagram things, that looks a lot like sort of accumulators, finite state accumulators. And in fact, we can modify this a little bit to change this into something that integrates a stream, or a finite state accumulator, however you like to think about it. So instead of the ones coming in and getting out the integers, what we'll do is say there's a stream S coming in, and we're going to get out the integral of S, successive values of that. And that looks almost the same. The only thing we're going to do is when S comes in here, before we just add it in, we're going to multiply it by some number dt. And now what we have here, this is exactly the same thing. We have a box, which is an integrator. And it takes in a stream S, and instead of 1 here, we can put the initial value for the integral. And that one looks very, very much like a signal processing block diagram program. In fact, here's the procedure that looks exactly like that. Right. We're going to find the integral of a stream. So integral is going to take a stream and produce a new stream. And it takes in an initial value and some time constant. And what do? Well, we internally define this thing int, and we make this internal name so we can feed it back, loop it around itself. And int is defined to be something that starts out at the initial value, and the rest of it is gotten by adding together. We take our input stream, scale it by dt, and add that to int. And now what we return from all that, the value of integral, is this thing int. And we use this internal definition syntax so we could write a little internal definition that refers to itself. Okay. Well, all sorts of things we can do. Let's try this one. How about the Fibonacci numbers? We can say define fibs. Well, what are the Fibonacci numbers? There's something that starts out with 0, and the next one is 1. And the rest of the Fibonacci numbers are gotten by adding the Fibonacci numbers to their own tail. So there's a definition of the Fibonacci numbers. How does that work? Well, we start off and someone says, gee, compute for us the Fibonacci numbers. And we're going to tell you it starts out with 0 and 1. And everything after the 0 and 1 is gotten by summing two streams. One is the fibs themselves, and the other one is the tail of the fibs. So if I know that these start out with 0 and 1, I know that the fibs now start out with 0 and 1, and the tail of the fibs start out with 1. So as soon as I know that the next one here is 0 plus 1 is 1. And that tells me that the next one here is 1, and the next one here is 1. And as soon as I know that the next one is 2. Right, so the next one here is 2, and the next one here is 2, and this is 3. Right, so this one goes to 3, and this is 5. Right, so it's perfectly sensible definition. Right, there's a one-line definition. And again, you could walk over to the computer and type that in, exactly that, and then say print stream the Fibonacci numbers, and they'd all come flying out. See, this is a lot like learning about recursion again. See, instead of thinking about recursive procedures, we have recursively defined data objects. But see, that shouldn't surprise you at all, because by now you should be coming to really believe that there's no difference, really, between procedures and data. And in fact, in some sense, the underlying streams are procedures sitting there, although we don't think of them that way. So the fact that we have recursive procedures, well, then it should be natural that we have recursive data too. Okay, well, this is all pretty neat. Unfortunately, there are problems that streams aren't going to solve. Let me show you one of them. See, in the same way, let's imagine that we're building an analog computer to solve some differential equation. Like, so you want to solve the equation y prime dy dt is y squared, and I'm going to give you some initial value. I'll tell you y of 0 equals 1, and let's say dt is equal to something. Now, in the old days, people built analog computers to solve these kinds of things. And the way you do that is really simple. You get yourself an integrator, like that one, integrator box. And we put in the initial value. Y of 0 is 1. And now, if we feed something in and get something out, we'll say, gee, what we're getting out is the answer. And what we're going to feed in is the derivative. And the derivative is supposed to be the square of the answer. So if we take these values and map using square, and if I feed this around, right, that's how it's a little block diagram for an analog computer that solves this differential equation. Now, what we'd like to do is write a stream program that looks exactly like that. And what do I mean exactly like that? Well, I'd say define y to be the integral of dy starting at 1 with 0.001 as a time step. And I'd like to say, or that says this. And then I'd like to say, well, dy is gotten by mapping square along y. So define dy to be map square along y. So there's a stream description of this analog computer. And unfortunately, it doesn't work. And you can see why it doesn't work. Because when I come in and say define y to be the integral of dy, it says, oh, the integral of what? Huh? Oh, that's undefined. So I can't write this definition before I've written this one. On the other hand, if I try and write this one first, it says, oh, I define y to be the map of square along what? Oh, that's not defined yet. So I can't write this one first, and I can't write that one first. So I can't quite play this game. Well, is there a way out? See, we could do that with ones. See, over here we did this thing ones. And we were able to define ones in terms of ones because of this delay that was built inside, because constream had a delay. Now, why is it sensible? See, why is it sensible for constream to be built with this delay? The reason is that constream can do a useful thing without looking at its tail. See, if I say, this is constream of 1 onto something, without knowing anything about something, I know that the stream starts off with 1. That's why it was sensible to build something like constream. So we put a delay in there, and that allows us to have this sort of self-referential definition. Well, integral's a little bit the same way. So you notice, for an integral, let's go back and look at integral for a second. So you notice integral, it makes sense to say, what's the first thing in the integral without knowing the stream that you're integrating? Because the first thing in the integral is always going to be the initial value that you hand it. So integral could be a procedure like constream. You could define it, and then even before it knows what it's supposed to be integrating, it knows enough to say what its initial value is. So we can make a smarter integral which says, aha, you're going to give me a stream to integrate and an initial value, but I really don't have to look at that stream that I'm supposed to integrate until you ask me to work down the stream. In other words, integral can be like constream. It can expect that there's going to be a delay around its integrand, and we can write that. Here's a procedure that does that. Another version of integral, and this is almost like the previous one, except the stream it's going to get in is going to expect to be a delayed object. And how does this integral work? Well, the little thing it's going to define inside of itself says, I'm a constream, the initial value is the initial value, but only inside of that constream, and then remember there's going to be a hidden delay inside here, only inside of that constream will I start looking at the delay, what the actual delayed object is. So my answer is, the first thing's the initial value. If anybody now asks me for my tail, at that point, I'm going to force that delayed object, and I'll call that S, and I do the add streams. So this is an integral which is sort of like constream. It's not going to actually try and see what you handed it as the thing to integrate until you look past the first element. And if we do that, then we can make this work. All we have to do here is say define y to be the integral of delay of y, of delay of dy. Right, so y is going to be the integral of delay of dy starting at 1. And now this will work because I type in the definition of y, and it says, oh, I'm supposed to be the integral of something I don't care about right now because it's a delay. And these things. Now you define dy. Now y is defined. So when I define dy, you can see that definition for y. Everything's now started up. Both streams have their first element. And then when I start mapping down, looking at successive elements, both y and dy are defined. All right, so there's a little game you can play that goes a little bit beyond just using the delay that's hidden inside streams. Questions? Okay, let's take a break.